Hey Geometry, I am on page 25 in our book and I am working on our video for section 3.1. So we're going to take a look at kind of a different approach to our math world, and this is where we start looking at the baby steps of a geometric proof and really understanding some different geometric terminology. So this is a little bit of a different intro to this section. Up here, it talks about how geometry is an axiomatic system. So first off, axiomatic system is kind of an overwhelming statement. Oh, and I'm recording from home, so you're going to hear some background noise. I've got some laundry in the dryer because I always have laundry going. Because when I'm working from home, it's evenings, nights, and weekends, and, well, I got to do laundry. So an axiomatic system means that we're going to have a certain set of things that really aren't exactly defined. We just know what it means, and then from there all definitions are based on that. So from a small basic set of agreed upon assumptions, things that we understand, and premises, an entire structure of logic is devised. And I know that that's blurry. My equipment has been not happy today, but I have to get my videos done or I'm going to be behind. So hopefully I only have to record this one. I had a pre-calc video I had to do 8 times because the equipment kept failing. So fingers crossed this is a one and done kind of thing. We're not going to address that very first part because, you know, it's not the best example. Let's see if I can angle this. There we go. So I want to take a look a little bit further down on page 25. So in an axiomatic system, we're going to start with some standard agreed upon assumptions and premises. And for us right now, we're going to talk about some undefined terms in geometry. We are going to talk about a point, a line, and a plane. And we understand exactly what these terms are. We know what a point is, we know what a line is, and we know what a plane is. It's just kind of hard to draw on a flat two-dimensional piece of paper. So, array. Our task is to use this language to define array. Well, we know what array looks like. It's like an arrowhead with a specific starting point. So what we can do with that is we can say that array is kind of like half of a line or part of a line. So it is part of a line with one end point. Well, that makes sense. It's got an end point, and the rest of it is basically a line. It extends forever in one direction. Okay, that kind of makes sense. So we use the concept of a point and a line to extend our understanding of geometry and use those ideas to describe other things. Collinear points. So I want you guys to look at that little suffix of linear, means line. Co means like company or cooperate, to share. So when we talk about collinear points, these are points, so using that initial concept of a point, that are all on the same line. So again, we've extended our knowledge to the concept of collinear points, but we're utilizing these basic geometric terms. Okay, coplanar. Well, if co means same or to share, plane means planar. When we talk about coplanar points, these are points. So again, using that basic word, I'm thinking functions in terms of pre-calculus, but it's not a function. That basic word, that basic term, that are all on the same plane. Okay, so let's turn the page. We are going to kind of do the same thing up here. Oops, too far down. Where an example is an angle. We understand that we can define an angle as 2 rays, and 2 rays have endpoints and line portions that go on forever. So we're going to officially define the concept of complementary angles. So they are 2 angles whose measures have a sum, remember that means to add, of 90 degrees. And that should clear up here in just a second. It's kind of awkward writing in the book because we're so early into the book that the pages fold over so much. Supplementary angles will be two angles whose measures have a sum, remember again means to add, of 180 degrees. Okay, so hopefully we're kind of getting that once we define something, we can use that term to define the next piece of the puzzle, and then our vocabulary just kind of grows upon itself. So our task now in this section is a little bit different. Our task is going to be learning how to do a step-by-step algebraic proof. And in this step-by-step algebraic proof, we are going to review some of our algebra skills and at the same time build some of our geometry skills. I'm actually going to scoot over here to page 27, and I want to walk you guys through an example of an algebraic proof. So I'm jumping the gun a little bit here where I'm showing you some extra things that we haven't addressed yet, some of the properties, but we're going to get there. So just kind of bear with me if you're like, oh, it's been a long time since I've remembered how to do that. A couple of things when it comes to working a proof. Notice how this is set up, and you can see the one underneath, where we've got two columns. On the left-hand side, we have what we call statements, and those are going to be our steps. And on the right-hand side, we have our reasons. So in this example, our task is to show that this kind of big, messy equation will eventually let us prove that x equals -3. So in the very first step, we start off with a given equation. So you know how we always have to write down our original problem? Our reason when we write down the original problem is given. And then in the next step, well, what changed? I'm hoping you guys can see that this 1 was added to the other side of the equation, so that it's gone from the left and the 11 increased to a 12. Well, then our reason is the addition property of equality. Okay, let's be honest. To write down the addition property of equality, that's going to be a bit annoying. That's a lot to write. It's okay if you guys abbreviate that and just write add. I will understand what you mean by the addition property of equality, because we added a 1 to both sides. If we look from step 2 to step 3, our parentheses disappeared. Well, hopefully we can see that what's happening is we're distributing through those parentheses, because 3 times x is 3x, and 3 times 2 is 6. Well, our reason is the distributive property, but it's okay with me if you use DIST, because that's what the abbreviation would imply. Let's look at the next step. Well, where'd the 3x go? It's no longer on the left, and the 5x was reduced. I'm hoping we can see that we're subtracting 3x, and you'll notice that we have a subtraction property of equality. It's totally okay if you abbreviate that and just say subtraction. Don't do SUB, because we have a specific math property that deals with substitution, like to trade something out. And that also kind of looks like the abbreviation of SUB, and I won't know which one you mean. So don't abbreviate subtraction. You have to write the whole thing out. At the next step, I'm hoping we can see that the 12 is gone. Well, it looks like it got subtracted. So another subtraction step. You don't have to write property of equality. It's just too long-winded. And then in the next step, the 2 is gone and the 6 is reduced. Well, that would be division. And I'm totally okay if you abbreviate that as DIV, because that makes sense. And then, this is something we're going to talk about. Okay, it kind of feels like we're done, because we just proved that x is -3, but we didn't. We proved that -3 equals x. And see how that does not exactly match? And I know you're thinking, oh, woman, you are picky. I'm not picky. Geometry is picky. This isn't in the right order. So we can flip things. When we flip things, that's called the symmetric property of equality. And it's okay if you abbreviate it as SYM. Totally fine with me. So it has to match what we were told to find. So that's a preview of what's to come. Over here, there are a ton of properties. And I'm going to utilize this space right here to talk about them, but I'm going to abbreviate. So addition. I am hopeful that we could agree that if we have A equal to B, couldn't I add the exact same thing to both sides and keep that equation in balance? It's true. We can add things to both sides of the equal sign as long as we add the exact same value on both sides. The same concept with subtraction. On subtraction, you can subtract the same identical value from both sides of the equation. Multiplication. We could multiply the exact same thing on both sides of the equation. Same thing with division. I'm going to make an assumption here, which I know is a little bit dangerous, but I'm going to guess you guys are pretty comfortable with that in terms of solving equations because we've tortured you with a lot of equations to solve in Algebra 1. Let's move forward. Let's talk about the distributive property. So the distributive property. Let's do it with numbers. Let's go 3 times 5 plus 2. Now I know order of operations would say, well, figure out what 5 plus 2 is inside your parentheses, and it's 7, and then multiply by 3. But we could also distribute through where we say 3 times 5, and then the 3 times 2. Well, 3 times 5 is 15, and 3 times 2 is 6, and that's 21. Isn't that the same thing as 3 times the 7? Yes. And there are times where we have to understand that distributive property, because what would happen if we had 3 times x minus 9 with the x minus 9 in a quantity, which means inside the parentheses? Well, we'd have to do 3 times x and then 3 times 9, and that would become 3x minus 27, and in that case we'd have to stop because there's no equal sign for us to keep going. So that distributive property is when we're sending things through parentheses. I'm totally with you if you're going to say the reflexive property really doesn't do much for us. It says that, I'm just going to abbreviate. That's not an abbreviation, that's a scribble. That the reflexive property just says like 8 is equal to 8. Well, why would you need that? Honestly, not right now, but we'll be needing it a little bit later. Symmetric. Okay, the symmetric, sorry, it is really hard to write on my book because it's scooting in. The symmetric property says like x equals 3 and 3 equals x. It says that we can flip things across the equal sign. The transitive property says that if you know two things are the same, like, let me show you with some numbers. Let's say that a equals negative 4. And then if I tell you that negative 4 is equal to b, well, a is negative 4, b is negative 4, then can't we say that a and b are going to be equal to each other? Yeah, because they're both negative 4. That's that concept of the transitive property where you've got two things equal to a third item. If you kind of just squeeze them together, then those two ends will match each other. And then the substitution property, well, technically the transitive property is like a double substitution. The transitive property just means that we can trade things in and out. So if I were to have x plus 5, but I were to tell you that x equals negative 1, I could substitute negative 1 in place of x and then simplify. Okay? So here comes our task. Using these properties, we're going to go over and we're going to solve an equation. And I'm going to try to angle this up a little bit better. We're going to pop down here to b. So we are going to, and I wish it told you what to prove. I just kind of feel like it should. We're going to put that in for ourselves. We're going to prove that x equals 2. And I just totally cheated and looked at the teacher book because I have not solved this problem this quickly in my head. So it better be right. Okay, we're going to prove that x equals 2. So we're going to create a column. It's going to kind of be like a table. We're going to have our statement, and we're going to have our reason. And admittedly, this would be easier on my notebook paper because we're going to number them. So the very first thing we're going to do is we're going to write down our original problem. and we're going to say that's what we were given. I'm going to draw a line because I need to be really organized. So step number 2, this is where people get a little bit frustrated because you have multiple ways you can solve this equation, and this is where I wish we were all sitting in the same room together looking at the whiteboard and I could hear you give me suggestions. So my first question to you out there in remote learning land that you can't answer because I'm not allowed to do new learning on a Zoom call, it all has to be recorded and I'm not allowed to record the Zoom calls. Well, here we are. What would be your guys' first step? And I'm going to guess maybe, because I personally can see 5 different first steps that work, but I'm the math teacher. I'm hopeful that we could agree that we could subtract 9 from both sides. So if I do that, the 4x remains on the left, 18 minus 9 is 9, and then negative 1/2 stays. And so that was subtraction. And you guys don't have to do this, so I'm going to highlight it in orange just to kind of show that it's optional. I'm just going to write the minus 9 so that you guys can see what I did. Now the next step, I could see some of my students saying, well, we have to get the x's on the same side. And then I could hear almost everybody saying, yeah, but that's a fraction, and fractions, I don't like them. You would have a couple of choices here. Debating what's the best option for us. My first instincts are let's get rid of the entire fraction because nobody likes them, but I don't think I'm ready to show you that just yet. So I'm going to add the 1/2 over. So 4x plus 1/2 x is 4 1/2 x's. And I'm going to write down my reason as addition. And technically it's the addition property of equality, but no one's going to write all that crap. Okay. I'm going to show you an extra step in here. Nobody likes 4 1/2. Could you write it as 4.5? Sure. That is step number 4. Well, did we do anything? We didn't move anything across the equal sign. We didn't do anything. We rewrote something as itself. That's where the reflexive property comes in. 4 1/2 is the same as 4.5. But we have to document it. Oh boy, I'm going to run out of room. Okay, 4.5 times x is equal to 9. Couldn't we divide both sides by 4.5? And if you grab a calculator, which is totally fine with me, you're not going to bother me if you grab a calculator, what is 9 divided by 4.5? 2. Done. Are there other ways to solve this? Yes. Would those other ways be accepted? Yes. I know that some of you guys in your algebra classes have been told that there's only one way to solve an equation, and that is not always the case. There can be multiple different ways. I know this video is long. I apologize for it. I'm just debating what more I want to do. This is probably going to be a 25-minute video because I want to do another one. Okay, guys, let's look at this example. So on this example, we are given kind of this overwhelming problem with 2 fractions. My dog's coming in the house, and she's probably going to try to come say hi to me. That, or my husband just got home, so you might hear some doors opening and closing. I don't have an office at my house. I work from my dining room table, so I'm just kind of in the middle of the world. So we've got these 2 fractions, and nobody likes fractions. So our first step is the given. Okay, right here, step number 2. Where'd the 10 come from? Well, I'll tell you that in just a second. But what's happening is that 10 is being multiplied on both sides of the equation. So that means that this is the multiplication property of equality. But why 10? Well, look at your denominators. The 2 denominators are 2 and 5. Isn't 10 the least common denominator? Yeah, it is. If we multiply both sides by 10, we end up reducing. The 10 and the 2 give us a 5, and that's where the 5 came from. And then the 10 and the 5 reduce and give us a 2, and that's where the 2 came from. So this step, a lot of my students would probably want to say reducing fractions, and that's not technically a property. Other people would say, well, what we did was we simplified. That's not technically a property. So what are we doing? I think technically when we reduce, 10 divided by 2 is 5. That's a true statement. That is a substitution piece. We're replacing 10 over 2 with the number 5. But you could also maybe go with reflexive because you're talking about the exact same thing. That's a lot of options. So know that if there's another way we can do something, we totally will. I'm looking at my screen. I'm like, it feels like there's something on my book. But it's not. I had a Cheeto fluff on my computer screen. It's gone now. All right, so from 3 to 4, the parentheses are gone, and the numbers got bigger. Well, that's a distribution step. When we distribute through parentheses, notice the 5 doesn't go across the equal sign. It's going just through the parentheses and stops, distributing through parentheses. In step 4 to 5, well, what happens here? The 2x is suddenly gone. Well, I think they subtracted that. And remember, I can't show that as SUB because that could be substitution. So we're going to talk about this as subtraction. And then the 15 got moved over. That would be addition. And then the 3 is gone, division. Now these are a little bit longer problems, and I warned you this was going to be a longer video. But we need to try a bunch of different examples. So let's take a look at number 7, and I'm on page 28. So Jeffrey wrote a 2-column proof to solve this equation. In addition to an incorrectly written prove statement, what error did Jeffrey make in his proof? Well, let's just walk through it. So that's the given. He wrote his problem down correctly. What changed from step 1 to step 2? Well, the 3's gone. So it looks like distribution. I think that's okay. From step 2 to step 3, well, the negative 6x, oh, if we add 6x to both sides, we'll get 9x, and that's addition. What's next? Well, on this one, don't we need to subtract? So wouldn't we subtract 15? And 6 minus 15, is that 9? Yeah. So that's a subtraction piece. Let's see. What else is going wrong? Well, so far, we're kind of doing okay. But how do we get rid of x? Shouldn't we divide it? So this should be division. And negative 9 divided by 9 is negative 1. So his proof statement, and I know that's blurry, I'm sorry, it'll get better in just a second. Please clear up. There we go. The proof statement was wrong, and we multiplied, divided, had that backwards. So sometimes we have to watch for errors. We are going to practice more of this, but I have to stop this video because, holy cow, this is kind of long at 24 minutes. We will do some more examples in our Zoom sessions on these. Please join our Zoom session. Alrighty, guys. Take care. Bye.